Welcome to the second part of lecture 18 of CS2100. In this second part, we are going to cover so-called Bernoulli trials that we can leverage to compute probabilities in games of chance. So let's see what Bernoulli trials are. So we'll start with an example that motivates Bernoulli trials. So suppose a baseball player gets a hit with probability 1/3 each time at bat. The trial is successful with H, which means a hit, and it fails with N, which means no hit. So the probability of H is 1/3, and probability of N is then 2/3. Let the event E be getting exactly one hit in 4 tries. So what is then the probability of E? So to compute E, we have to analyze all possible sequences that lead to this outcome. And there is going to be 4 of them. And now we have to use the product rule to compute the probability of each case. And it's going to be 1/3 for hit times 2 to the power of 3 to the power of 3 for no hit for each of these cases. Because these cases are mutually exclusive, then we can use rule of sums with no overlap, and we can compute the total probability by summing these 4 times, which amounts to 4 times 1/3 times 2/3 to the power of 3. Or if we think about it slightly differently, that's choose 1 out of 4. So we are computing how many possible sequences there are times the probability of each sequence. And so that gets us the final probability. So this leads us to the theorem called Bernoulli trials. So given a simple experiment called the Bernoulli trial and an event that occurs with probability P, let the event E of n, k be the probability of having exactly k successes in n repeated independent trials. And then the probability of this event E of n, k is choose k out of n times p to the power of k times 1 minus p to the power of n minus k. So it's easy to prove this theorem that is also kind of inspired by the previous example. So let's assume that outcomes of each trial are from the set S, F. Then each possible event has k s's and n minus k f's, and therefore it has the probability p to the power of k times 1 minus p to the power of n minus k. And there are choose n k of n ways that give us this result. So it's really easy to derive this theorem. So let's see how we can use this theorem in a couple of examples. So the first example we have is related to coin tosses. Suppose we have a loaded coin that gives heads with probability 4/7. Now our question is, what is the probability we get 8 or more heads in 10 tosses? So we are going to split this into 3 cases. In the first case we have 8 heads, the second case 9 heads, and in the third case 10 heads. And we are going to use the theorem that we just introduced to compute each of these cases. So probability of getting 8 heads is choose 8 out of 10 times 4/7 to the power of 8 times 3/7 to the power of 2. And in similar fashion, we can compute probability of getting 9 heads and probability of getting 10 heads. Because these cases are mutually exclusive, then the probability of getting 8 or more heads is their sum, which is roughly equal to 0.126. So this example illustrates how to use Bernoulli trials. Okay, here's another one. I'm a big fan of Utah Jazz, and so I really like this example. So suppose the Jazz win a game with a probability of 0.75. Then the question is, what is the probability that they win a best of 7 playoff series by a margin of 4-2? So let's denote with J a Jazz win, and with O other teams win. So this series must be exactly 6 games, and it has to end with a J. Of course, the series always ends with the team that wins the whole series winning the last game. And now, how many possible sequences we have for these first 5 games? Well, that's C of 5,3 because we have to place 3 J's into 5 slots. And then the probability of each sequence is 0.75 to the power of 4 times 0.25 to the power of 2. And then the total probability of Jazz winning 4 games to 2 is, if we plug it into our Bernoulli trials theorem, this expression, which evaluates to 0.198. Okay, great. So let's look at one more example. And this one involves a World Series. So in 1992, announcers said that in the previous years, the team that won the first of the best of 7 series won the entire series 60% of the time. And the question is this surprising or not? And now that we know how to compute Bernoulli trials, we can assess whether this is surprising or not. So first, let's assume that both teams are evenly matched. So that means that the probability of TA winning is equal to the probability of TB winning is equal to 0.5. And now let's suppose that team A wins the first game. So now the question is, what is the probability that A wins the series in 4, 5, 6, or 7 games? As in the previous example, notice that A must also win the last game. So here I sketched out different configurations that lead to A winning in the best of 7 series. So in the first one, we have to place, it means A won all 4 games, and so we have to place only 2 A's here, so there is only one way of doing it. And so the probability of this first one is 0.5 to the power of 3. Probability of the second one is choose 3,2 because we have to place 2 A's in these 3 slots times 0.5 to the power of 4. And then the third one and the fourth one we compute in a similar fashion, and we get the final probability to be 0.66. So as it turns out, what the announcers announced as something that should maybe be surprising is not surprising at all. Because if you assume that teams are evenly matched, we get the probability of 66%.